Tonight is November the 14th, 2018. What I'm going to do tonight is just a couple of quick experiments, make these as efficient and hopefully effective as I can. We're going to run a test on this Dynaco Mark III in very good condition. It's got a new board in here. I've had this for quite some time. I made some modifications so I can have a dynamic and a static balance besides the actual bias pot over there. So what I'm going to do is, the question was, does it change the frequency response to move an 8 ohm load from the 8 ohm tap to the 4 ohm and the 16 ohm? Well, right now it's on the 8 ohm tap. So what we're going to do is we're going to test it, because we can test frequency response. I can plot that very nicely and very accurately. What we're going to be doing right now is we're running this into these 8 ohm loads up here. These are two beautiful R-Call 8 ohm loads, 400 watts a piece. I think they're 300 watts a piece. Yeah, there's the 300. And they're low inductance, just a couple of micro henries of inductance in them. We'll be running it with this HP 8903. It will do a scan from 20 to 20 kilohertz. It is controlled by a PC. It has a device on the back here through this cable, GPIB, HPIB interface, or whatever you want to call it. And then we'll be watching the power right here. Okay, this program you can get off the internet for free from a site and a good gentleman by the name of Pete Millett. I'm not going to go over that. That is way too complicated for us to do right now. But I've got it set up for 5 points per decade at a generator level of 1 volt. That is 1 volt input into the amplifier, and I'm going to press start. And then it'll say, is my reference level okay? And I can either say okay, or I can cancel it and readjust it. I can readjust it by, changing the generator level if I want to change the power level. But right now, the reference level is about 21.5 watts at a kilohertz. That's our reference level. Now, we're going to start running it. We can run 4 traces on this. This is trace 1, 2, 3, and 4, and that makes it really easy to see. So we're going to hit run, or OK there. It'll start running. Now, see, there's our line. This is at 20 hertz. It's just right above 0.3%. It runs very, very nicely. It's really a beautiful amplifier. Now, the important thing to note right here too, sorry I got to go back and forth so much, but it's about 21.5 watts output. That's something we want to take note of. About 21 watts. And this thing is going to run all the way through from 20 hertz to 20 kilohertz. You have to put 30 in up here, but it'll actually stop over at 20. That's just a little glitch in the program, but that's not bad at all. Okay, it stopped right there. We run the whole thing. It's a little above 1%, about 1.1% over here at 20 kilohertz. So that's what it does for an 8 ohm load on the 8 ohm tap of the transformer. Now I'm going to stop the camera and I'm going to make the adjustment, and we'll come back and we'll run the second and then the third plot. Okay, now as you can see, I've got it on the 8 ohm load on the 4 ohm tap. Let's go over here. This program is so nice. We'll run it here, trace 2, and it'll start out. I think it's blue. There it is right there. There's the blue trace. It's below 0.2%. So it's actually quite a bit better. But look here, look what has changed. Our power. Our power's gone down about half, hasn't it? I think we were like 23.5 a while ago, now we're like 12.5. I mean, it's virtually a half. So, you would expect it to be somewhat better, even though it's into a 4 ohm load. Let's watch it run all the way to completion. And there she almost is. Right there. Just below 0.5% out at the other end at 20 kilohertz. Really nice plot. These amplifiers perform very well. Okay, now let's move it, the 8 ohm load over to the 16 ohm tap. Okay, now we have the 8 ohm load right here over on the 16 ohm tap. Let's run it again. We do trace 3 down here. We click on it, and it starts running. Starts at quite a bit higher. Actually, I can hear it humming over there. But let's look at the power. It's up to 41 3/4 watts, practically doubled. How about that? Okay? I'm doing that just so you can probably hear the transformer. And look how it's going to run. That's not too good, is it? That's not too good at all. So does it change the frequency response? Well, I guess it does. It doesn't do much for changing the frequency response in the middle frequencies up to about, oh, well, not too high. Here's 1 kilohertz, 2, 3. At 3 kilohertz, it gets pretty weird. So will it change the frequency response of your amplifier? Well, in some ways, we got to say yes, and in some ways, that's not really the primary thing it does. The primary thing it does is change the power output dramatically. It halves and doubles it for all practical purposes. So there's the answer right there. That's what happens to your to a plot of THD when you change your 8 ohm load from 8 ohm to 4 ohm and then 16 ohm. This is 8 ohm. This is the proper load. This is 4 ohm, and that's the 16 ohm tap on the transformer. So there you go. Hope that helps answer that question. Okay, the only other thing we'll talk about tonight is I was asked a question of how do you determine how to put the phasing. How do you determine the phasing when you want to put like secondary windings in series? Here we have a 6.3 at 5.3 amps, another one 6.3 at 5.3 amps. If we want to put those in series, how do we know how to phase them? Well, unless you've actually got a diagram that's got some dots on there that shows you the phase, you don't really know. But it's not that hard to figure out. And the best way to do it, in my opinion, is just do it the old-fashioned way. What I'm going to do is hook up 120 volts right here to 1 and 3. That would be putting it across the 0 and the 115 volt winding. Let's connect this guy up quickly, and then we'll end up seeing that across our other windings. We'll see what we get. We want to stay away from 8, 9, and 10. That's 800 volts at 400 milliamps. That'll do you some real damage. We want to stay away from that. So let's plug it in now. Everything looks safe. If if measuring a transformer, a naked transformer like this, if there's such thing as safe. Okay, 13 and 14 right here we can see is 6 volts. And we'll look at our meter over here. This is 13 and 14. It's 6.8 volts. Of course, this is not under load, so if you load it down to 5.3 amps, I'm sure it'll hold up to 6.3. But we want 12, so how do we know which one to, how do we know how to jumper this winding to that? And the answer is we really don't. So we just experiment. Let's put this one, this for fun, over to here. Let's put it to that side. So we've got a winding here and we got a winding there. I don't think I need to draw that out. I think everybody can see that. Then we should have our 12 volts between here and there. And we have actually nothing. We have like 30 millivolts. So we did something wrong. Well, then let's jumper it to the other side. Let's jumper it to here and then measure across it. And there we go. That's how you do it. You just do it experimentally. There's no sparks, or hopefully not. If there's sparks, you're doing something wrong. Now you know how to put them in series. And now that you know how to put them in series, you also know how to put them parallel. So we've got high current. We've got 12.6 volts at 5.3 amps between here and there. I'm not going to short them together, but if we wanted to put them parallel, now that we know what is series, we put this one here, and then we put, I mean, we would do this, of course, with real wire instead of jumpers, and then we can put this one there. See, I got no sparks because they're in phase. And across here now, we still have we have nothing. And I've got, oh, well, it's plugged in. How can I have nothing? This can't be. Oh, I measured across the wire, I'm sorry. There's our 6.8 volts. Except now, instead of 5.3 amps, we got 10.6 amps. Now, I'm not going to do this because I don't like to blow the tips off of my... when I was a kid and I didn't have a meter or whatever, I would do it the real old-fashioned way. And you could put this one here. And in a real emergency, since you know that 13 and 14 is one 6-volt winding, 15 and 16 is the other one, and then you can put the other one right here and smack it against it, and you'll get some pretty big sparks out of the other side. I don't want to do that, and the reason I don't want to do that is because you end up messing up the tips of your things. They look really ugly. Okay, now that we got that one in series, we've got another 6-volt winding. It's only at 3.5 amps. That's on 17 and 18. We could jumper this one to here. And then let's measure and see what we got. We should have 18 volts now if we did it right. And I don't know if this is right or not. And we have, there we go. All right, I lucked out on it. So now we got 18.9 volts under load. Let's see right there. But if we jumpered it over, but if we made the mistake and jumpered it to the other side, then we got 12, but we're going to subtract 6 because we put 6 out of phase with it. I think we're going to get 6. And yeah, we got our 6 volts back. That's just the way I do it. There's just no sense in getting out an oscilloscope and trying to determine phase and whatever. I mean, you can do it that way. That could be a lot of fun. But if you just want to figure it out, that's the way I do it. So I hope this helps. Thanks for all the suggestions. I'm trying to keep these nice and short and simple and right to the point. So let's just keep moving. Be safe.